Hello, welcome or welcome back to my YouTube channel, and today is day 3 of our statistics video series, and hope you enjoyed last 2 videos. So today is like lesson number 3. We are going to dig into probability, sampling distributions, standard error and central limit theorem. So I need to tell you that this is where statistics starts becoming powerful. And also like these are the foundations of that we are going to learn today. These concepts are the foundation of confidence intervals, p-values, hypothesis testing, regression, survival analysis, which are most important statistics concepts in medical researchers or other researchers. So like everything you have learned so far, I mean mean, like median, standard deviation, IQR. So everything you learned so far describes a data set. These things describe a data set, right? So now we move to inferential statistics. So that means we need to make a conclusion about the entire population using a sample, right? So that means we use a sample. So these things are based on not on an individual value. So these things are mean, median, standard deviation, IQR. These are describe a data set which has individual values. So but these are this probability, sampling distribution, standard error and central limit theorem. These are based on a sample. That means we are going to make conclusion about an entire population. For that we use sample, right? So okay, then let's start from topic number 1, that is probability. So this should be very probability. So this should be very familiar to you. Like I mean intentionally, or like you are not intentionally asked this question from your kindergarten teacher or like preschool teacher, but sometimes you may ask, like you have asked this question, like will today rain or not? This is a probability question, whether even though even though you don't know that is like you didn't know that is probability question, because like there is only like 2 answers for that question. Like it is whether like will it is rain or not, then you have 2 answers, rain or not. That means you have only 2 answers, it is yes or no. So that means that is the probability. That means you have only 2 chances. That means half a like 0.5 for raining and 0.5 for not raining, right? So that means we measure uncertainty, right? So that means probability measures uncertainty. So it ranges from 0 and 1. That means in probability you have only 2 chances, that is 0 or 1. 0 means it is impossible, right? So 1 means certain. So that means you have only 2 chances, that is 0 and 1. Or sometimes we call 0% and 100%. Here also 0 means impossible and 100% means certain. So probability measures uncertainty, right? So for an example, this is a very popular example when you learn probability in school as well. So we'll refresh your knowledge. So the example is like probability of getting heads. Like when you toss a coin, then probability of getting heads is 0.5, right? And if it is a like rolling disc, then probability of rolling a 6, That is, you have 6 chances. That means you have 6 sides. Then getting a 6 means 1 out of 6, right? So these are the examples. And like I'll tell you a medical example. Suppose you have 100 patients receive a drug. Like 100 patients receive tamoxifen, right? Kind of 100 patients receive a drug. And among 100, 10 develop a side effect, nausea. So estimated probability of nausea. Then estimated probability. I'll mention it as P. Estimated probability of nausea is 10 out of 100. That means 0.10. That means again it is 10%, right? So this is probability. So you may wonder why probability matters. Why probability matters? Like medical research asks question like, what is the probability this treatment works? What is the probability this result happened by chance? Or what is the probability a patient has disease given a positive test? All of statistics is built on probability. So in that situation, probability plays a huge role, right? Okay, we'll move to the second concept, that is sampling. Suppose we want to know average height of all women in US, right? So we need this data, average height of all women in US. So can you measure that means can you measure height to get the average height? We need to know like each and every height of each and every person in US, each and every women, each and every female in US, right? So but it is impossible to measure everyone. So we take a sample, right? So since we cannot get since we cannot get the entire population, we will get a sample, right? So that means, for an example, we have 100 women randomly selected, right? So among all women in US, we will get a sample. The sample size is 100 women randomly selected, right? And then we calculate mean height, right? Calculate mean height. Maybe mean is, I don't know, but mean can be 162 centimeters, right? So that means instead of getting the entire population, we got this sample and then we calculate the mean height, because like practically we cannot get we cannot measure everyone, right? Okay, so there is a question, right? There is a question arise. So the question is, would another sample, that means we took this 100 women, that is the sample, right? So if we get another sample, like another 200, like another 200 women, this is another sample, or another 100 women, right? Another 100 women. This is not the same sample, right? This is not the same sample like this. Okay, this is another sample. This is sample 2. Think this is sample 2, right? My question is, would this sample give exactly 162 centimeters height? No. Maybe yes or maybe not. Maybe sometimes 160 centimeter or 164 or 161, right? Or any other value. So that means every sample is slightly different. So that means every sample is slightly different. So if you take 100 samples, then the mean value or the height can be different from each and every sample, right? Okay, the key idea is, now you need to know the key idea of this. So the key idea is samples vary naturally, right? This variable is called sampling variability. So that means samples vary naturally. That means we are getting a random sample, random group of people, right? So that means that because of that, samples vary naturally. This variation we call sampling. This is sampling variability. Okay. Okay. So the third concept that we are going to learn today is sampling distribution. This is sampling distribution. So this is one of the most important concepts in all statistics, and students often struggle here as well. Let's go slowly. Okay. So imagine population mean height. So imagine population mean height. Is we will assume 160. So you repeatedly take samples, right? So that means population mean height is 160 and you repeatedly take samples. Sample 1. So the mean is 158, right? And you get a sample 2. Then mean is 161. Likewise, you get sample 3. Mean is 159, and you take the sample 4 and mean is 162, and you get the sample 5, that means you are the last sample, and it is mean is 160, right? So now we can draw a graph of all sample means, right? So this graph, if we draw a graph like with all sample values, so that means this graph is called sampling distribution of mean, right? Sampling distribution of mean, right? If you draw a graph of all sample means, that means these values, this graph is called sampling distribution of mean, right? So this is very important. This is not a distribution. This is not a distribution of people. It is a distribution of sample means, right? So that this is not a, keep in your mind, this is not a distribution of people. Not a distribution of people. Instead, this is a distribution of sample means. This is a distribution of sample means, right? If you draw this graph, this is not a distribution of people, this is distribution of sample mean. So because we got the sample mean values. Okay, now we have two concepts, that is sampling distribution and population distribution. So population distribution, we need to get an idea about the difference. So population distribution and sampling distribution. Sampling distribution. So what is the, that means in population distribution contains individual people, right? Individual people. That means person 1, 155 centimeters height. Person 2, 170. Person 3, 162. Likewise. Now sampling distribution contains sample means. So that means sample mean 1, 158. This is not someone's height. This is sample mean, right? This is a person's height. So, and sample mean 2, 161, right? Sample mean 3, 159. So, this is the difference between population distribution and sampling distribution, right? Okay. Now we are going to learn an important concept, that is central limit theorem. Central limit theorem, or we call CLT. You can see this in research papers as well. So this is probably the single most important theorem in statistics. That means it explains why most statistical tests work, right? This explains why most statistical tests work. So theorem is like this. Theorem is, if sample size is sufficiently large, the distribution of sample means become approximately normal, right? If sample size is sufficiently large, the distribution of sample means becomes normal, right? So even the distribution of sample means become approximately normal, even if the original population not normal. Original population may not be sometimes not normal. But if the sample size is sufficiently large, the distribution of sample means become normal, right? It may not be like exactly normal, but approximately normal, okay? This idea is somewhat revolutionary. Imagine population income highly skewed, right? Imagine population income. This is highly skewed. Now you learned these concepts in large like previous video. That is skewed, like means right skewed, left skewed, right? So that means population income is think that it is right skewed, right? So that means population income is highly skewed. However, it is highly skewed. That means it is not normal, right? And you are taking 1000 samples. This is a huge number. You are taking 1000 samples, and after that you calculate mean income for each sample. You are going to calculate mean income of each sample of this 1000 samples, mean income. And after that, the distribution of these those means become bell shape. Bell shape means, you learnt in last video, that is the bell shape means normal, right? Even though population income is highly skewed, once you get a large number of samples, the mean income became normal, right? Bell shape means normal. I'll give you a visual idea, okay? Visual idea is this. Think population skewed, right? And you take many samples, right? Many samples. And then you calculate sample mean. And then sampling distribution becomes normal, right? This is the visual idea. So can you tell me why this is important? You may wonder why this is important. Because most statistical methods assume normality, right? And this central limit theorem allows us to use those methods, okay? Because most statistical methods assume normality, and using this central limit theorem, we can use those methods, right? So there is a rule of thumb. In practice, we use sample size is equal or greater than 30, right? It often gives a reasonable approximation. This is not actually a strict rule, but commonly we use this as a practice. The sample size is equal or less greater than 30. Okay, the next concept is standard error. Standard error. Now we arrive at the most misunderstood concept. Why I say this, like students often confuse standard deviation and standard error, right? So you learned standard deviation in the last video. So what do you measure in standard deviation? Standard deviation and standard error. You measure here measures variability among individuals. And in standard error it measures variability among not individuals but among sample means. Right? Not individuals. This is very important. So here standard deviation, for an example, ages 40, 50, 60, right? So standard deviation describes how different patients are from each other. Like this is patients' ages. So that means standard deviation describes how different patients are from each other. But here we are not going to take any individuals. Instead, we are going to take sample means like sample, right? In a sample. So think standard deviation answers how spread out are patients, right? How spread out are patients. But standard error answers how precise is our estimate of the population mean, right? How precise is our estimate of the population mean. Okay. So the formula is, now standard error formula is standard deviation divided by number of, this is n means number of samples, right? Number of samples. So here this is standard deviation. Now this is the equation, or this is the formula of calculating standard error, right? So you have to divide standard deviation by square root of number of samples, right? So then you will get the standard error. Okay, for an example, suppose standard deviation is 20 and sample size is 100. Then how you calculate? Standard error is 20 divided by, that means 20 divided by 10, that is 2, right? So the interpretation is here. The sample mean typically varies by about 2 units from sample to sample, right? That means sample mean typically varies by about 2 units from sample to sample. This is the interpretation here. So why standard error gets smaller? Now look at the formula. If you look at the formula, like if we increase the sample size, here this is the sample size. If we increase the sample size, that means denominator increases and the here SE decreases, right? Okay, so for that we can take an example. So n equal 25, SC equal 20. Sorry, SC equal 200. Okay, and n equal 100. Sorry, here a standard deviation equal to 100, and here standard deviation I'm sorry, that is not true. This is sample size is 25 and sample size is 100 and sample size is 400. Okay, and when you calculate standard error, standard deviation divide by here 5, then means 4. Here standard error is 20, and like you have to get this square root of 100, that is 10, and that means it is 2. Here 4, here 2, and here standard deviation is 20 and 20, then 1, right? So here 4, here 2, here 1. That means larger samples, more precise estimates, and smaller standard error, right? That means if you get a larger sample, that means your standard error will become smaller, right? That is the key idea here. Now here sample size is 25, right? And here sample size is 100, and here sample size is 400, right? So that means larger sample, this is the largest sample, then standard error is 1. This is the smallest sample and the standard error is 4, right? So if you get larger samples, then you can make your standard error very smaller, right? So that means more precise estimates. You can get more precise estimates. Okay. Hope you understand today's concepts clearly. If you don't understand, please ask from me, or else we can discuss this further videos as well. Okay, thank you for watching. This is the end of today's video. Bye.